the microphone. Is it on? Yes? There we go. There are two ways to get a really complicated mathematical problem when you're doing economics. One of them is to take a simple problem and add a bunch of real-world features to the model to try and make your modeling of the real world as realistic as possible. And the other one is to do dynamics. So buckle up. This is a talk about a very strong assumption that mainstream transaction fee mechanism design makes. And that assumption is that users are not willing to delay their inclusion in exchange for lower fees. So in the classical models like the seminal Rough Garden 2021, Chung-and-Chi 2023, the users arrive and they either get into the block or they immediately disappear. But of course, anybody who works on an actual blockchain knows that this is not the case, and that users have some users are time sensitive. So for example, if a user wants to trade on a DEX, then they probably want to trade at the current prices, not the prices in 5 minutes. If they want to trade, or if they want to do some payments, like at the coffee shop, you probably don't want to be waiting 10 minutes for your transaction to confirm because your coffee is going to get cold. And if you're playing something like chess or poker or other real-time games on the blockchain, you probably don't want to wait. On the other hand, there are some that are not time sensitive. For example, if I'm just sending some money to a friend, maybe I'm willing to wait 10 minutes or 30 minutes or an hour. If I'm posting some batches, oftentimes we see these L2s are willing to delay the posting of their data onto the L1. And in particular, a big use of gas on Ethereum mainnet is contract deployment. And in that case, devs are often willing to wait a very long time to do that. So this paper is basically going to try and unify the old world of transaction fee mechanism design with this new dynamic context where users face an explicit trade-off between faster inclusion and lower fees. And we're going to do that by adapting some of the queuing techniques in Huberman, Leshno, and Molemy, which is a paper that explicitly looked at the Bitcoin fee market in a dynamic setting and modeled it. And then we're going to extend that to discrete block times, deterministic block times like we have now after the merge in Ethereum, and to 1559 as well. So our main results, I would summarize the first one as proof of stake has better UX than proof of work. And the reason for that is because block times are deterministic. And the second one is that EIP 1559 price does not converge to the right price, which is something that I think we're only just discovering now, but is an interesting discovery based on the discussions that happened at the time it went in. It actually converges to a different price if the parameters are not set correctly. And we're going to talk about how to set parameters correctly and what the suggestions for what to do about these problems that I'm about to discuss are at the end of the talk. So just to go over the model, we're going to do a queuing model. Like I said, dynamics can get complicated, but I think we tried to keep the complications to a minimum. The number of new arrivals of transactions is going to be random according to a Poisson distribution with parameter lambda. And each transaction is going to be associated with a particular type of user. So you might have users who are more time sensitive or less time sensitive. And in particular, the way we model that is that each user has a vector of two things. One of them is theta v, one of them is theta c. And theta v is their total willingness to pay for the transaction. So that might be like, I want to pay $10 to get this transaction on chain. And theta c is the delay cost per unit time. So if I am delayed 5 minutes, I get theta v minus 5 minutes times theta c. And we're going to assume that those are distributed according to a distribution f on the interval 0 to c bar. So transactions are going to be served. Oftentimes in these queuing models, we have two things. We have the arrival process and the service process. So you go to the DMV. the rate at which people arrive at the DMV is the arrival process, and the service process is the rate at which the clerk handles the activity that you're trying to do at the DMV. And so this is now moving on to the modeling of the service process. And this we're going to model as a chi-square distribution, which sounds a little bit weird to do. With 2p degrees of freedom, you can see the density there. The reason we do that is because we want to be able to model both exponential arrival from proof of work and deterministic arrival from proof of stake. And it turns out when p equals 1, you get exponential, which you can check. And if you want deterministic, you do this tricky thing where you take the limit as p and u tend to infinity with the ratio constant, and you get deterministic. And again, that's so that we can model the different arrival processes in proof of work and in proof of stake, which is particularly relevant for Ethereum, which is where I spend most of my time doing research on, which actually moved from one to the other. And so this plot is actually a plot of the transaction, of the block wait times 1 week before the merge and 1 week after the merge on Ethereum. So we can see the difference right here. One fun fact, actually, the block time went slightly down. It was about 13 seconds on average before the merge, and it's 12 seconds after the merge. So this theorem comes basically straight from revenue equivalence, and so you can see the information rent term here. But this is about the Bitcoin fee mechanism, which we're calling pay your bid here. And this theorem originally appeared in the Huberman et al. Paper that I described earlier. And basically, W star is the equilibrium wait time as a function of the equilibrium bid B star, which is, of course, a function of your wait time. And importantly, it's a function of your theta C, the cost of waiting, not the value that you have of getting the transaction on chain. And what does that tell us? Basically, what matters here is your impatience, not your total value. So you might have a contract that you think is $1 million if you deploy it, but if you're not impatient, you shouldn't be willing to pay very much. That's basically what that's saying here. And a corollary of that is that we can back out the equilibrium wait time in this pay your bid mechanism as a function of the effective load, which is a quantity that depends on the arrival process and the departure process, which you can see here. So this theorem appeared in Huberman, like I said, and you can see that in a batch service process with exponential arrivals, which is based on a priority queue, we have the equilibrium wait time here, and we have the equilibrium bid here. So this is where we extended from the results of Huberman, where we showed with deterministic using that chi-squared distribution limit trick, the equilibrium wait times and equilibrium bids when block times are deterministic like they are in proof of stake. So let's dispense with the symbols and look at the charts. Like I said earlier in the talk, I'm going to show you that proof of work has worse UX than proof of stake. And so you can see here with one transaction in the block k equals 1 and with 2 transactions in the block k equals 2, and what's nice is we were able to get actual analytic closed forms for these that we're plotting. These are not simulations, they're analytic closed forms. You can see that the equilibrium bids, which are a function of the wait time, are longer in exponential block arrival. What's some intuition we can use to think about this? Basically, what's the equilibrium wait time when you submit a transaction in Bitcoin? How long are you expecting to wait for the next block? It's always 10 minutes because that's the memoryless process, the exponential arrival process. But when you submit a transaction in Ethereum, which is a deterministic block arrival process, if you submit at 6 seconds, there's 6 seconds left to the next block. So it actually depends on when you submit, and the average is only half of the block time. And you can see that these are roughly, half of one another. So I would argue that that's most of what we're seeing here, although obviously there's a lot of complexity in the math. Okay, now I'm going to move on to our exploration of 1559, which of course is even more interesting now that Ethereum has both deterministic block times and 1559 fee market. Here, let me just go through a quick explanation of how this works. It's pretty simple. We have a gas limit, which is 30 million gas. If a block has 30 million gas, it's full. We have a gas target, which is half of that, 15 million gas today in Ethereum. And if the block is more than half full, we increase the price of gas, the base fee. If it's less than half full, we decrease the price of gas. So according to this formula. And we keep doing that, and I guess the logic is eventually this should converge to the right price, the equilibrium price, the shadow price of what people are willing to pay. And one thing we know, I should have put it up on this slide here, but there's a paper by Leonardo et al. With Barnaby Monod and Thomas Thierry on it as well, that was showing that we get the right amount. So remember I said we have a gas target. Well, if you have a target, we probably should hit it, right? So that showed that even if there was crazy stuff going on with how these guys jump up and down and the price didn't necessarily converge or was chaotic, we still got the right amount. But that still leaves the question of, did we get the right price? And the current folk intuition is like, we're using the right amount of gas, so shouldn't we get the right price? But here's a problem with that intuition. Let me show you an example. So in this example, we have 15 million gas of transactions arriving every period. Half, so 7.5 million gas of that demand is theta t equals 0, basically no, like completely patient, infinitely patient. And then the other half is extremely impatient, with a disutility of 1 for every block that they wait for inclusion. So in this model, there are two pricing rules that both use 15 million gas on average, which remember I told you we know we use 15 million gas with 1559, but have very different utilities and prices and revenue. So in the first one, we price the inclusion at 0. After all, that's the shadow price, right? Because we have 15 million capacity on average, and we have not enough people willing to pay for that. In the other rule, we charge 99 cents for a fast lane immediate inclusion, and $0 for inclusion if you're willing to wait 1 block. So this is basically like a monopolist price discriminating against the people who are impatient. And in this case, the impatient transactions pay 99 cents. They get included immediately, but every patient transaction pays 0 and gets included in the next block. And these are very different equilibria, but they both use 15 million gas. So, and one of them has much higher revenue than the other one, which I guess Justin Drake would be quite happy about. The thing we're going to argue is that 1559, when parameters are misspecified in particular, but even when they're correctly specified, has a problem where it can lead us to a similar outcome as that situation. There's some jumpiness in the price. It can make it so that periodically we have holidays where if you wait 1 block, you'll get a much lower price. And patient users will be willing to wait. Impatient users must pay the current high price. And we look similar to the simplified model that I just discussed. So let's see if we can see that play out. Well, this is actually 1,000 blocks, so about 3.5 hours, 3 1/3 hours of actual data from the 1559 mechanism on Ethereum. You can see the blocks that we're referencing here. You can see that this is quite spiky. And I will give full disclosure that I chose a very spiky one. But the point here is that this happens quite frequently. We're spiking from 40 gas or even lower all the way up to 65 or 70 gas in some cases on like these very short time intervals. So if you're patient, then you should just wait for one of these valleys here. But if you're impatient and you arrive when there's a spike, you have to pay the price available at the time. And so what we would argue is basically 1559 is higher revenue than the priority pay your bid mechanism because of this reason. And we're going to do an explicit model of that. We're going to consider 2 prices for simplicity. Again, we're already doing dynamics here, so we can't get too complicated. We're going to do high and low price, and transactions are going to be either high and low willingness to pay. And we're going to simulate that. And as you can see in that simulation that we did, the X and Y axes here are the load of low impatience transactions and the load of high impatience transactions. And you can see with just changing the fee mechanism, nothing about the arrival process, the wait times of the low types, which are the people who are patient, are much different under 1559, much higher under 1559 than they are with a priority fee. And so we start to approach that simplified model that I showed before, where in many cases, if you're impatient, you're willing to wait, which again wasn't modeled in the kind of seminal work of Roughgarden and Xi and that whole thread of literature, because it was all a static model. And here we're explicitly considering impatient and patient users, and we start to see a very key difference between 1559 and the priority fee. And I just wanted to give a shout out to Potas here, who a lot of people consider us enemies on Twitter, but I wouldn't consider us enemies. But I think I really agree with this sentiment that Ethereum is not a company. We're not a profit maximizing company. We're trying to build a system that has very low friction, as low friction as possible. And we should not price resources in order to accrue value. We should price resources in order to not be denial of service attacked. And we should have the minimum price that nodes can handle on the target hardware. And if we're using a fee mechanism that raises the price, that kind of is in direct contrast to this. If we're using a higher revenue system than the one we could use, that's certainly something that we should consider alongside the other benefits that, of course, 1559 does have, including dominant strategy, incentive compatibility, UX, and stuff like that. So let me talk about where do we go from here? What should we do about it? Here's the splurge part of the roadmap that Vitalik tweeted in December. Great name. You can see that endgame EIP 1559 is not very filled in yet. So I'm going to attempt to add a little bit of color to that and maybe move it along a little bit, and what I would suggest we do from here. So like I said earlier, like the problem of spikiness in this graph here, this is a problem that is exacerbated if the parameters delta, which is the tuning parameter of 1559, how fast it updates, is overtuned. And right now I think it's overtuned. And so here's an argument. Basically, what could we do is we could all sit down on core devs, and every hard fork we could try and tune it. And I think that's a bad equilibrium. I don't think that sounds very much like endgame to me. That sounds like adding a lever that somebody has to tune in perpetuity. So I'm going to give an argument for a auto tuning mechanism within Ethereum. So here's how that would work. Basically, if we see this situation where we have a full block, then we update the price, and now the block is less than half full, that's a sign that our updating rule was too aggressive. Because what we should really be trying to do is, given the information we have today, set a price tomorrow that is expected 15 million gas use. That's the gas target. We should expect to hit the gas target on average. And so every time we see this, we're going to decrease delta by a very tiny bit. On the other hand, if we see this kind of situation where we have a mostly full block and then another mostly full block, that's a sign that we should have probably incremented the price a little more to be more towards the gas target. And if it's even, then delta seems pretty good. Good job, delta. We'll keep you there. And so what does that look like? Basically, this Python code would implement a 2-parameter 1559. Now we have a 1-parameter. So we'll have a delta, and we'll have a delta prime. And we will very slowly adjust delta over the course of 2 weeks to be whatever is correct. So let me go back to this, because I think this is kind of the money shot of the results that we have here, and close out. I think the takeaway I would say is that we've shown that with some good intuition here, you can see that 1559 and priority fee are very much not the same mechanism. It's not as if 1559 is the DSIC version of priority fee. They have trade-offs that we should consider, and we should consider whether we want 1559 at all, because priority fee has some advantages. But if we do want 1559, one thing we can do to bring them closer together is to tune the parameter appropriately. And we don't really want to tune the parameter on core devs every hard fork. So we should probably put something in the protocol that tunes it. And another thing I would add about that, there's these moments that we change the network substantially. So we do things like we do the London hard fork where we introduce 1559, or we do things where after the London hard fork we did proof of stake, and then that changed from deterministic to, or from exponential to deterministic arrival. So those are like big changes that we do. Recently we did 4844 in March. And these are big changes to the fee market. And so we need to adjust when we do that. And the best way to do that is auto leveling, as we suggest. So I'll be releasing an EIP soon and targeting it for the next hard fork after Pectra. And hopefully I convinced you guys that this is a step towards the EIP 1559 endgame.
We have time for a couple questions, if you line up there. First question, Max, I guess, is one way to think about the proposed change to 1559 that if you think about it as a PID controller, right now it just has a proportional term and you'd be adding a derivative term?
Yeah, exactly. And I guess I'm an economist, so I don't know what a PID controller is, but like that sounds about right. There's a question of why don't we add more derivatives, right? So my goal is to have 1559 with the right parameter to kind of mimic us setting it on core devs and do it very slow updating. The goal is not to like have it be changing during the day and during the night, which you could want to do. I also think that adding a bunch more derivatives, because it's kind of like a slippery slope argument, why don't we just add infinite derivatives and make the protocol more complicated? It's basically, there's some manipulation that can happen when you start to hit the second derivative and third derivative and stuff, and it does add more attack vectors, which to an already very manipulable market.
I guess I'm going to riff on that. I am, in fact, a controls engineer. So the question was actually going to be about introducing a controller and the fact that you're addressing a particular parameter by introducing a controller which has more parameters, which inevitably is the case when you want to create a closed loop system and regulate a set of properties. But building on the question about the derivative control, I think derivative control in general can be destabilizing. And so in order to actually get a system that is sort of self-calibrating, I'm not sure that the approach is going to work quite as nicely to eliminate the future calibration. If you set that as your primary goal, I think that there are like classes of controller that might be a better suit to that objective. So I guess the real question was going to be, is your primary objective to create something that doesn't need to be calibrated, or is your primary objective to sort of change the stochastic equilibrium of the gas levels to hit a specific target? Because those objectives could actually come into direct tension with each other. And so like even fleshing out the requirements so that you're directly trading off in your controls design, with the emphasis here on, it seems like the good solution for Ethereum would be something that's kind of self-healing, maybe not necessarily as efficient, but if your goal is to avoid needing to calibrate, it's a different class of controller.
Yeah, I think that's great, and I think there's a lot more discussion to do as we continue to scope it out, and I'm not married to the derivative approach. I think if you look at what I showed, it's not just that we're trying to calibrate the derivative, it's actually we're trying to do something which is, we're trying to make this more like a martingale. So I would argue that I'm not just slapping on a derivative, there's a very specific intent behind it, which is that, but I'm really happy to chat more about specifics and would love to chat more, and we're certainly not tied to the exact PID controller implementation or whatever. I think that we would be happy if there's a better idea to do that as well.
Thanks for your time and presentation. I'm an ex-controls engineer, so I love the PID analogy there. But I'm also a finance person, and I want to bring that perspective here. You said earlier in the beginning that some are paying too high fees and others are paying too high in wait time. But that's to assume that fees and wait time are fungible. But to many users, is it not the case that they're actually not fungible? And some people actually would rather pay in wait time. Thank you.
So I have an interesting perspective on this. I actually work at Consensys, which is the parent company of MetaMask. And one interesting thing that we see with users is we give them 3 options, like a fast, a medium, and a slow. And like 95% of users just choose the medium option all the time, which is interesting from my perspective, because it seems like when I write down this model, then I think the users should probably at least be aware of whether they're fast, medium, slow, and even smart contracts, which are huge, oftentimes fill up a whole block and cost $500 or something. You'll see if you go and look at what they clicked based on their gas that they used, it's actually the medium option, which it should be the slow option. So that's an interesting question. I think in this particular context, the priority fee still makes it so that the users who are willing to pay more go first, because it's just a first price versus this posted price system. So in some ways they are fungible. They're not fungible on Solana because they don't have a working fee market, but on Ethereum at least we have a working fee market, even if it is charging users a lot and delaying people.
Thanks, Max.